Last couple of classes, we've been looking at solving numerically partial differential equations. Today is another class solving partial differential equations. This kind of summary slide over these past few classes. Why am I solving these particular differential equations, partial differential equations? I picked the Laplace equation from electrostatics. I picked the diffusion equation, an application in thermodynamics. I'm going to today pick the wave equation and an application in mechanics. I didn't really pick them so I could cover electrostatics and thermodynamics and mechanics. I picked them as different classifications of partial differential equations, sort of the important classifications of partial differential equations. So that was the purpose behind that. Is 2 classes ago, Laplace's equation from electrostatics. We solved that. That was a partial differential equation in space, not time. We solved it as a partial differential equation in 2 spatial variables, 2 independent variables. We moved on to solution of the diffusion equation. That was a partial differential equation in time and space. So the way we solved it as a partial differential equation, again involving 2 independent variables, the time variable and the space variable. And then what we're going to do today is a third partial differential equation, the wave equation. It's also a differential equation in space and time. We're going to solve it again with 2 independent variables, the time variable and then 1 space variable. The point is that these involve different forms of first and second order differential equations in space and time. And kind of they are the sort of space that you would typically meet of partial differential equations in space and time. Let me say a few more words about that on this slide. So these 3 partial differential equations, Laplace's equation, diffusion equation, and wave equation, cover 3 distinct categories of partial differential equations. And they're given names, elliptic, parabolic, and hyperbolic. Kind of impart an analogy. If you remember conic sections, elliptic, parabolic, and hyperbolic are conic sections. If you remember in motion under gravity, right? There's elliptical orbits, parabolic, and hyperbolic orbits. So drawing on analogies for that, there's 3 classifications of partial differential equations. The Laplace equation is one of them. The diffusion equation is the second one of them. And the wave equation is the third one of them. So they're respectively the elliptic partial differential equations, parabolic and hyperbolic. What they differ in is one way of thinking about them is how information propagates in time. So in the Laplace's equation, that differential equation, the solution of that differential equation, is actually a static solution. And if you were to change the boundary conditions on the Laplace's equation, that information would propagate instantly through time, immediately through time. And it's not a wave equation it's not a partial differential equation that's evolving with time. So that's our elliptic classification. What about the diffusion equation? We call that a parabolic equation. In that equation, that is a function of time, but function that changes in time evolve smoothly and they relax or die out over time. So that's the characteristic of a parabolic partial differential equation. If you were to change the boundary conditions on a parabolic equation, like the diffusion equation, actually those propagate instantaneously. Their effects propagate, although it is a time-varying diffusion equation, the changes of a boundary condition at some level propagate instantaneously. The third type of category is the hyperbolic category. The wave equation is an example of that. In this particular case, we've got a wave equation that, again, like the diffusion equation, unlike Laplace's equation, is a function of time. In this case, it's a function of time that is not kind of steady and relaxing. Rather, it emits a wave, a traveling wave. And in this case, information propagates at the speed of the wave at which the wave travels. So that's that third category. I wrote down here for these two equations that involve both space and time coordinates, the diffusion equation and the wave equation, some statements about the stability of numerical solutions. So for a stable numerical solution, these are the two conditions. This is for the diffusion equation, and this is for the wave equation. So they relate the steps in space and time, delta x's and delta t's here. And these conditions have to be met when you choose your steps in space and time. These conditions depend on your space and time steps and a sort of coefficient of proportionality between the space and time parts in the differential equation. That's the diffusion constant or the velocity of the wave in the two partial differential equations. And if you don't fulfill these conditions, your numerical solution will be unstable. Basically, if you don't fulfill these conditions, what you're emitting is high frequencies into your solution, and high frequencies become catastrophic in your solution. When you discretize space and time, you're restricting the frequencies that are embedded in the solutions, and you're going to have to fulfill these limits on your space-time increments to get a stable solution. Okay, so as an example of a wave equation, we'll take this one from mechanics, and I'll just walk through something I'm sure you've met before, which is the derivation of the wave equation for a wave on a string that's under tension, and it tells us the speed of the wave on a string under tension. So it's all based on this little picture upstairs here. I've got a wave in blue that's stretched between two walls on either side, or two bookends on either side. The length of the string, we're told, is this uppercase L. The density, the kilograms per meter of the string. So the mass per unit length of the string is the rho. We're going to imagine that we displace the string from the horizontal by some amount. I called it y in this slide here. So that's kind of the dependent variable. The position along the string of the displacement is the x. That's the independent variable. And we're going to build up a wave equation for y as a function of space and time, as a function of x and t. So that's our goal here. To the plot, I added a little element of the string or the cable or the wire that we're going to consider. So a little element here, dx, or a little section dx. To that, I added the tension forces on that little element that are going to cause that little element to move over time. And that's based on that little element and the forces acting on it is how we're going to uncover the wave equation, how we'll solve the wave equation. So as a starting point, I've got Newton's second law here, F equals ma. I've cast it in the form of the problem with the string, right? So rather than talking about mass m, I'm going to use the quantity here, the mass density, the mass per unit length times the length of the little element as the language for expressing the mass. So that's mass here. Here's the sum of the forces over on the left-hand side here. Now we're going to be thinking about the forces in the vertical direction. We're interested in the wave-like motion in the vertical direction. So some of the vertical forces. And here's the acceleration, written as the rate of change of the rate of change of the position, the vertical position. So that's a Newton's second law. That's our basic start point. I filled in the two forces that are acting on the little element. At least I filled in the components of the two forces that are acting on the little element in the vertical direction that's going to make the wave-like motion. So there's a tension pulling in my sketch here to the left and a bit down on the left-hand side of the element. And then there's a tension on the right-hand side is pulling to the right and a bit up on that element. So I've just filled in those tensions here. So it's the horizontal, vertical components of the tension is this T sine theta here. And the vertical component of the tension is the T sine theta for the right-hand side. This is theta is varying along the length of the wire. So this is the thetas at these two different ends of the wire. So these thetas is slightly different in my sketch. These thetas will be different. And so that's what's going to create a net force on it. So here I just replace the thetas, sine thetas, using the small angle approximation, so that sine theta is roughly tan theta is equal to dy dx, the rate of change vertically over the rate of change horizontally. So I made that little replacement here. And then I spotted that actually what I've uncovered is that this rate of change of the slope is nothing other than the curvature, the second order differential with respect to x. This would vanish if there was no curvature of that wire. But there is a curvature of the wire of the cable. So, and what's emerged here is that curvature. And at that point, we probably made a partial differential equation, which is the wave equation. So this is the wave equation. We just uncovered it. Basically, it was hidden inside Newton's second law. We just had to uncover it from Newton's second law by just plugging in what the forces were and rearranging them. It also tells us, remember that a wave equation has this particular form here, these two second order differentials with respect to space and time, and the coefficient of proportionality in front of the spatial part. That's physical interpretation of that is the square of the speed of the velocity of the wave. It's going to tell us that the square of the speed of the wave's velocity on the string is the tension divided by the mass density, mass per unit length of the string. Okay, so that's the wave equation that we're going to be working with, and we're going to solve that numerically today. I just want to talk a little bit on a couple of slides here I got about the analytical solutions. Again, one reason we're picking the solutions we did with the Laplace equation, diffusion equation, is we could check our numerical solutions against analytical cases. These are the sort of cases where we can solve them analytically. How would we go about solving the wave equation for the string analytically? Or we would go ahead with the method that we've used before, which is to separation of variables. We speculate or hypothesize that the solution to our wave equation, reproduced here, has a form that you could write as a product of a separate function of the space coordinate and a separate function of the time coordinate. So that's going to be my speculation or guess or hypothesis. I'm going to try that out and see what solutions emerge from that particular hypothesis. So I'm going to plug this idea into the wave equation. So if you imagine plugging in or replacing f, the function of both space and time, replacing that with this product of these two functions that are a separate function of space and a separate function of time, called uppercase X and called uppercase C. I plug those in. Of course, if I'm plugging in them to the spatial derivative, then the function that depends on time can just be pulled out of the spatial derivative because it's independent of space. And likewise, if I'm plugging them into the time derivative, the part that depends, that is a function of space, can be pulled out of the time derivative because it's independent of time. So I did that. And then I divided through by the product of the two functions themselves. And when you do that, you discover this little result here, that you've got one term which is just a function of x, and it doesn't involve time. Another term that is just a function of time, it doesn't involve x. And for the wave equation to hold, these two functions must be equal to one another. And we're just going to call that that quantity that they're equal to this separation constant. We use this separation constant K to define that quantity. So this means that no matter what the spatial coordinate is, this combination of the spatial coordinate function and its second order differential, that must always be the same. So x, uppercase X varies with x, and that combination of uppercase X is differential and the function itself is position independent. Likewise for the time function. Uppercase T is a function of time, but this combination of uppercase T's function of time and its second order differential, this must be independent of time, so we can write this constant. And that's what allows us to break out the two equations into, the one partial differential equation into two first order differential equations. So these two familiar equations. These are equations that familiar throughout physics. These are equations we probably recognize the solutions to. That if I think about the equation on the left for x, uppercase x, it's an equation that says the sum of the weighted sum of the function of x itself and the second order differential of x, that adds up to 0. So that prescribes what the function is. And we know, for example, if you think about a sine function, you differentiate that twice, you get back the sine function with a negative sign. So the sine functions would fulfill that differential equation. The same is true over here for the function of time, right? Again, it says that the second order differential of that function of time plus the function itself, weighted in a certain way, will add up to 0. And we know that a sine wave would work for that, or other cosine wave would work for that. And so here I wrote down kind of the general solutions to these two equations. The general solutions have a lot of parameters associated with them. There's the separation constant K, or this omega here is involves K and C. So it's if you define K, you've defined omega. So that's a constant that defines kind of the frequency of the wave number of the wave-like solution. And then there's all these coefficients A, B, C, and D that correspond to all the different families of solutions to the wave equation. I can at that point multiply the two solutions together and we get the general solution that has this particular form here. when you write it like this, you can see that you either get in the exponent, when you combine the products of the exponents, you either get a minus sign or a plus sign, and then physically there's minus signs and plus signs, so corresponding to waves traveling in the positive or the negative direction. So that emerges out, that solution is that there's two sets of waves, traveling to the right, traveling to the left. Okay. So, sure you've all met that before, but that's a reference point in the analytical solutions for the wave. We've discovered that the string, the string under tension, has a Basel wave equation. And we've discovered that that wave equation leads to solutions, the whole families of solutions where you have a wave that could be traveling to the left or traveling to the right with a certain characteristic speed is determined by the tension which the string is under, more tension, faster speed, and the mass density, mass per unit length of the string. The larger the mass density, and the slower the wave will travel. So we've uncovered all those features, and now we're going to go on and numerically solve the problem. We should be at a reference to the analytical understanding of this problem. Okay, so in numerically solving the problem, just like in the Laplace equation, we had to turn the Laplace differential equation into a difference equation. In the diffusion equation, we had to turn the diffusion differential equation into a difference equation. And here, for the wave equation, you have to turn that differential equation into a difference equation. And we had prescriptions for doing that. In all of those differential equations, all we ever saw in the differential equations was either a second order differential representing the curvature of some function, or a first order differential representing the slope of some function. So those differential equations were all just statements about relations between curvatures and slopes of functions. That's what they came down to, just a mathematical expression of relationships between curvatures and slope. In the wave equation, it has this form that the second order differential of the solution, function solution with respect to x is in proportion to the second order differential of that solution, that function, with respect to time. So it's just two second order differentials, one with respect to position coordinate, one with respect to time coordinate. So those second order differentials are saying that the curvature with respect to space of the function is in proportion to the curvature with respect to time of the function. And all we've got to do is turn this math language from curvature with respect to space and time for the analytical function to difference equations for the curvature. And if you remember that to write the difference equation for the curvature, it has this form here. So this is the form for the curvature with respect to time, and this is the form with respect to curvature with respect to space in a difference equation. So what I've done in the difference equation is I've gone ahead and I've discretized space and discretized time. H is my units of discretized time. A on the right-hand side is my units of discretized space. So that's my lattice in space and time. It's defined by A and H. To determine the curvature in space is this combination of the value of the function at some location in space and its values at its nearest neighbors to the left and right. This combination picks out the curvature. For example, if the function was not curved, if it had no curvature, it could have a slope but no curvature, then this sum is zero. It simply means that the point in the middle is the average of the 2 points on the left and right. That's having no curvature. If the point in the middle is not the average of the 2 points on the left and right, then there is a curvature, and it could be positive or negative. Same thing with respect to time. If we think about some moment or instant in time, the value of the function of some instant of time, then the value of the function at a prior moment and a later moment, it's this combination of those three values of the function at those three adjacent moments in time on your lattice that determines the curvature. Again, if there is no curvature with respect to time, it just means that the point in the middle is the simple average of the points on the later time and the earlier time. And if there is a curvature, it means that that value of the point in the middle is not the simple average of the later time and the earlier. So this is the substitution that we need. Now what I have to do is plug this into the wave equation, and we get this difference equation. So this is difference equation corresponding to the wave equation. It's got quite a few terms in it because it's got terms referring to the function at some moment, some position here, and its two neighboring positions. Then it's got the value of the function at some time here, and its two neighboring times, earlier and later. So it's certainly a different difference equation from the diffusion equation and the Laplace equation. Here I just rearranged it. There were 6 terms in there, and at least there's 6 values of the function at different points in space and time in that differential equation. And I've rearranged it here such that on the left-hand side is the value of the function at some point in time in the future. And it's the value of function at that point in time in the future in terms of the current value of the function. So at the earlier time, at the same point in space, but also its value at other points in space, neighborhood. This is just that equation rearranged, and it can be used as a prediction for the function in a future time. Yeah.
I'm sorry, is nu the linear density?
Say that again.
Is nu the linear density? Oh wait, no.
V, yeah, this is actually a V. Sorry, this is the speed of the wave.
Speed of the wave.
Yeah. So all these coefficients here that go back. It's fine. Well, we wrote down the curvature with respect to space. We picked up the square of your spatial increment, and with time, the square of your time increment. So we get these factors, and we already had a square of the speed of the wave and the wave.
That's just the way it works.
Yes.
Okay, that makes sense. Thank you.
Yes.
Okay, my question was, I just got back and I saw a bunch of letters, and I was just wondering if all you did was you just took it to the other side.
Yeah, that's all I did.
Yeah, I could see you did that.
Yeah, that's all I did. I've taken, yeah, I did that. So, at one place in here, these guys here, right in here, is the value of the function in the future. It's this one here, right? And so I just made an equation for that. And all the other ones are the current or past values. Okay. So we have this equation, and this is how you could imagine solving the wave equation numerically by calculating the future value of the wave on the string at some future time in terms of the current value of the wave on the string, current time. But actually also what's new here also involves an earlier value of the wave on the string rather than the current time. So in the diffusion equation, we were taking the current value of the temperature along the length of a rod and then calculating the future value of the temperature on the length of the light rod. So we just need the current temperature distribution. We calculated the future temperature distribution. Here's a little bit more complicated. To calculate the future wave on the string, we need both the current wave on the string and for the previous increments, the prior wave on the string. So we've got to go back not just to the current time, but the prior time. That's because our differential with respect to space is second order, meaning a curvature, rather than first order in diffusion equation, meaning a slope. So for the curvature, we're going to need two earlier points in time. For the slope, we only need one earlier point. But anyway, we're going to go ahead and use this. This is just to help in imagining. So this plot here is meant to show this two-dimensional space-time lattice. The horizontal dimension is the length of the string. So these are the little increments of the string. These are the little mass increments of the string horizontally. And then vertically is the progression in time. These are little time increments. So it's space, horizontal, time vertical. We're starting on the top row. So the top row is like the initial conditions on the string. So imagine like guitar string, you're going to pluck it, it's that moment. And then each row below is successively later and later times as you see this, the wave travel along the string. The function, the wave function evolve on the string. Here's a moment I'm capturing in the calculation where I'm going to calculate this time, this value of the wave function at this position. So I'm wanting to calculate this. So it's at some moment in time, and it's at some location on the string in this discretized space. Who do I need to calculate this? I need to look back for the future time, and I need to look back at the current time. And actually, I need both the value of the function at the current time in the same location, and also at the two neighboring locations, to the left and right. So that's what these are here. But I also need, as we just saw, not just the current time, but I need information from the time increment before that, the prior time. So this goes into the calculation too. So this detail looks different for the diffusion equation. It looks different for the wave equation because of the differences in a slope versus a curvature at first order versus second order differential equation. There's one wrinkle here. Let me mention it. What about the very first step? So the very first step, I've indicated it in red upstairs there. So the very first step, well, you have the current values of the position of the string. Imagine you pluck the string, that's your initial conditions. You have those. What about, but you're going to need the prior values. And what we're going to assume is that the string was actually held there stationary, so that the prior value for that first step is just the same as the initial conditions that you're going to use for the current step. So that's that very first step, we're going to have to, in the program, implement it specially because we don't have a prior step. We just have the current step. So we'll do something slightly different there. And so I'm summarizing here the two equations that we're going to be using. This is the one from the last slide, which is the full equation for all the steps except the very first step. This is the equation for that very first step. And all I've done is said that the value of y at the prior time, this one here, is going to be equal to the value of y at the current time. And so this 2y minus y becomes just this y here, because these y's are the same for that very first step. Oh, the other thing I wanted to mention here is in green on the right and green on the left. So this is a boundary condition. You've got your string, and we're going to imagine that your string is affixed to some wall or these bookends. So at the far left and the far right, we're going to enforce, as we propagate away, we're going to enforce that the string is unable to move at those two locations. So that's a boundary condition. Now that's a choice of the type of problem I'm solving. I could have, the string able to move at the two ends of the string. So that would be an open-ended string rather than a closed fixed string. Or I could have one end open, one end closed. So that would be another problem too. So I'm just picking as an example the case where the two ends are fixed. Okay. Any questions on that? If not, I'll just go on to the code and we can walk through some of the code.
So basically, we run through the whole string first just to get the initial conditions, basically, and then we run through to get the time evolution.
Yeah, I would say that we set up the initial conditions everywhere on the string to begin with. So in that sense, we do. I mean, because as a program, we're implementing.
Right, because it can't just be a delta function right at the place where you pop the code. That's the.
Yeah, I mean, it could be.
It could be.
Yeah, you could. I could say, well, I mean, it would be hard to imagine it.
Right.
But you could say, well, my first deflection is that I'm just going to displace this one little element. I think that would be perfectly valid. You see how that propagates, right?
Okay.
And that, so that would be one example of an initial condition. I'll show you what my example was. One that's more like actually getting into guitar string and plugging them.
Right.
But you could pick any initial condition. You could pick the initial condition that is a perfect sine wave on the string, right?
Yeah.
Set up. I mean, then it would.
Right. That does make sense.
Yeah.
Okay. I just thought because it was like non-physical, but I guess.
Yeah.
It could be.
You could make it. I mean, you make it physical by saying that, well, we discretize space. And so I can move just one.
That's true.
One little element.
Right.
Yeah.
Right.
Yeah. Okay. So we've got a few parameters in the problem, two parameters related to the string, three important parameters related to the string. Well, we listed them all before. We had the length of the string is one important parameter. I'm just going to work with 1 meter for the length of the string. The two other parameters that came up in the wave equation were the tension under which the string is held and the mass per unit length of the string. So these are the T and the rho. And that just picks some numbers for the T and the rho. 4 newtons is the tension, and here 10 grams per meter for the mass of the string. So I just made these numbers up. But look, say the tension and the mass density, they're going to have an important influence on the wave on the string because they really control the speed of the wave on the string. So you would be able to make this wave go, you could explore this, right? Experiment. You can make the wave go faster or slower by changing those two parameters. Speed is V is square root of T over I. Anyway, so I've set these parameters up and because we had also solved it analytically. We go to discretize space and time. This is the discretization of space and time like we did for the diffusion equation. I think I just cut and paste this. I'm going to have 100 elements in space. So I go 1 meter long wire or cable or string we divided into hundreds, so little 1 centimeter segments. I've got a discretization in time. I made this 10 milliseconds, quite short in time, so 10 to the minus 5 a second. These quantities have to obey that stability that I've mentioned. It's a relationship between delta x, or in the language here, a, your spatial increment, and delta t, your language here, h, the time increment. And if I remember in my head correctly, delta t divided by c delta x is going to be less than 1. That's the stability condition. And that, I'm not deriving that, just quoting that. The derivation of that comes from that you've got to avoid problems with having a space-time grid that emits very high frequencies, which cause instability. So that avoiding the instabilities by very, very high frequencies leads to this condition, stability condition. It's called a von Neumann stability condition. And there's stability conditions for the diffusion equation. Anyway, these are still it's not a problem. When we're using the difference equation, all these quantities like linear density and tension and speed of the wave, they all boil down into the difference equation to one combination of them. Is this combination? We had a similar thing in the diffusion equation. It was a slightly different combination because we had a first order differential instead of second order differential with respect to time. Calculating that.
I see. I'm sorry, I seem to remember V topic where in your work. Right? Maybe
In the differential equation?
Yeah.
Hope I wrote in the differential equation, it's a V squared is the coefficient between the time derivative and the space derivative.
Right, because it's C squared in the.
Yeah. Okay. So, I mean, there may be a typo on the slide, but I couldn't remember. Okay.
Sorry, can you repeat the stability condition?
The stability condition, if I remember, it's written on slide number 2, but I wrote the stability condition for both the diffusion equation and the wave equation, but I think it's written as delta t time increment. It's got to be smaller than delta x, c delta x. And say that again. B delta x.
Yeah, I think
and it's all about that if you make delta t too large, you emit high frequency component. If you did a Fourier decomposition of your solution, right? Your solution has many frequencies built into it. When you discretize the lattice, you cut off a bunch of frequencies, right? You chop them off. If you do that incorrectly, you keep high frequencies and you make the solution unstable, unstable. Okay. We've got all our parameters defined now. We want some independent and dependent variables or proxies for independent and dependent variables. And we want to set up our initial conditions and boundary conditions. So we've got to do those two things. And then we can do the calculation. So look, here's a proxy for an independent variable. This is the x position along the length of the wire, just defining that. Here are proxies, 3 of them, for the displacement of the wire vertically. I didn't pick the names very good. Well, the big Y, Y1, Y2, but we need the prior time, the current time, and the future time. So that's what these are going to correspond to. I should have called them something appropriate. Um, we've got to, anyway, so we have these arrays, these are proxies that independent variables. Now we've got to set up our, as we were talking about, our initial condition for the wave on the string. We're going to plot it in some way. Maybe I could have picked the delta function, or maybe I picked the sine wave, but this is what I picked. Is just a triangular wave. I'll show it to you shortly. So this is really a little bit of ugly code because it's a lot of numbers rather than symbols representing things. But basically, I'm setting up a sawtooth-like plot of the string. Specifically, what I'm imagining is, suppose I've got this meter length of string. Here it is, my arm. I'm going to 4/5 of the way along of the meter, so 80 centimeters of the way along. I'm going to move the string by a centimeter up. And so now I've got this weird sawtooth shape, and I'm going to release it. And we're going to see how that propagates in the wave equation. So this would be a difficult problem to solve analytically, right? Because it's a sawtooth. But it's very easy for us to solve this or any other shape of initial condition numerically. So this is kind of the numerical approach rather than the analytical approach. The analytical approach is beautiful for looking at your general solutions or looking at simple sine waves or harmonics on the wave, but for a practical thing of plucking a string, not so good. We can do that. So I'll show you the plot of this, but basically this 80 is where I put my 80 centimeters is where I put my finger. And the amplitude, these equations create a sawtooth that has amplitude of 1 centimeters and is peaked at this location of 80 centimeters. Okay. Let's walk forward. If I walk through the code a little bit, I'm going to print out some numbers just as reminders, but I'm going to plot what the wave looks like at that very first moment so that we can see it. And then after plotting the wave at the very first moment, I'm going to do one little calculation, which is where I step that wave forward to the next increment. The reason I'm doing that very first step as a separate step is, remember, it had a separate equation because we didn't have a prior time, we only had a current time. So we made a separate equation, assuming that the wave was basically, the string was not moving when we released it, that its position at the prior time was the same as the current. And so this for loop here is a loop over the length of the string. And it's calculating this next moment in time for the position of the wave on the string based on the current and the initial conditions for the wave on the string. So this is the equation. And then, so I'm going to move the wave forward one time increment. And every time I move it forward, I'm going to have to update these arrays for the timing increments, right? So here's me updating the arrays for the timing increments. I'm going to make, let's see what I've got here. Go back the other way.
No, I explained you that often.
Oh, sorry. This is me just copying, sorry, I'm having trouble getting back to this location. Copying forward the arrays and also copying forward the boundary conditions, enforcing the boundary conditions here. This is, I learned the hard way, you have to be a little bit careful about, signing things. If I didn't either use the copy function here, which I think, or this slicing, which seems like you're slicing everything, you don't actually copy the data. Rather, you just assign the variable to the old location. So this literally does copy forward. Okay. Having done that, this top plot here is the initial location of the wave, and this second plot here is the wave after this first clock. And well, look, they look almost exactly the same. They're not exactly the same. You see that the wave propagates, but they look exactly the same because my time increment, I think it was just 10 milliseconds. So if you imagine plucking this guitar string and looking over a period of 10 milliseconds, the change is going to be very small. But maybe I'm real close up. It looks like there's a little bit of a curvature on the top here that wasn't upstairs here. So this has changed a little bit here. In the next cell, I'm going to increment the time by many time steps. And so I just pick 100 time steps to increment. Instead of just going forward 10 milliseconds in time, I'm now going to go forward 1 entire second in time, 100 of these 10 millisecond time steps. So I'm doing that with this nested loop here. The inner loop is the loop over the position on the wire, where I calculate the future time from the prior time, and the outer loop is where I'm just stepping forward 100 time steps. Inside the inner loop is now this second version of the difference equation that we want to use for every step except the first step. So this is the one that was a little more complicated in these first two terms. We've got this guy. Okay. So I'm going to run this. We're going to take 100 time steps. Every time step, we're going to calculate the future position of the wave based on the current and the prior position of the wave. After we do that, we have to keep updating our variables here. That's what this line is doing. Our future time becomes our current time. Our current time becomes our prior time. That's the problem that's going on here. And we've got to keep enforcing our boundary conditions. Okay, so this is after plotting the wave after I've gone forward 100 steps, so 1 second. And so we had a triangular wave, a sawtooth wave, and we start to see how it's changing along the length of the wire. And it kind of looks like it's propagating down the length. So that's what you're seeing here. In the next cell, I put in another loop. Okay, I've got 3 time elements going about. I've got the time increments, the time steps, which is 10 milliseconds. I've got a unit of time steps that was 100 time steps, that was a whole second. So I, in the last case, went forward at 1 whole second, 100 time steps, and made a plot. I'm going to do the same thing here. But I'm going to call those 1 second intervals. I'm going to call those these time epochs. And I'm going to go forward 10 of them. So now I'm going to go forward 10 10 seconds, every second of the 10 seconds, I'm going to plot the wave on the string. And every 10 milliseconds, I'm going to be calculating the updated position of the wave on the string. So this is these three nested loops here. Inner one, again, is just at a moment in time, we're going to calculate the future position of the wave from the current and prior positions of the wave. The one in the middle is just to evolve us through 100 of those steps to get what happens in 1 second. And when they plot, these plots are plotted every second. And then the outer one is just to step forward 10 of these epochs so that we can see the wave over a period of 10 seconds.
So I'm sorry, can I just see I'm just trying to get together the labels Y2 and like how you rename them. So for just any given cycle, just Y is sort of what we're iterating. And then Y2, Y1, okay. So
yeah, that's good. I got a feeling I may have my comment on the very side may have been bad. And let's look at it here.
Okay.
Y is the future time.
Right.
Because that's what we calculate.
The next one, yeah.
This is the reason I should have named it sensible. I should have said Y future, Y current, Y prior, right? This is Y is just the future.
Yeah.
Y1 is one, which appears a number of times, and it appears at the location of Y to the left and right. Y1 is the current location, right?
Okay.
And then this Y2 here is the prior location. And it's the Y2 only appears at the location I, not I plus 1 and I minus 1. So Y2 is prior, Y1 is current, and Y is future. So downstairs here, when I'm doing this copying, I'm making Y, which I've calculated as the future, I'm going to turn it into the current. Mm-hmm. And I'm going to take Y1, which was the current, and I'm going to turn it into the prior. Okay, so I copy those over, and of course I'm going to calculate the future. So that's what I'm doing here. That's also why what I'm setting here, I'm setting on the boundary conditions on the next future position. So I set them here. So that's the meaning of Y, Y1, and Y2. Saying them that way, we're going backwards in time. This is the wave now. So these are epochs. We'd already gone forward a second epoch. Epoch 1 represents the wave after traveling 2 seconds. And then 3 is 3 seconds, so we'll get down to 11 seconds here. And if you remember the wave after 1 second, and it looked like this. Had this little section here where it was evolving with respect to time. Now you can see that growing and what's going to happen to it. So it's like that where we pluck the wire, the information about that pluck is sort of propagating from 80 centimeters from the pluck over here to the left and right. So that we did something and released it. It's propagating along the length of the wire in these 2 directions. If you're over here at 2 seconds, but you don't know that the wire has been plucked yet, released yet. And if you're over here at 2 seconds, you also still don't know the wire has been released yet. coming soon. But you don't know here and here that the wire was released. It's just in this region. This is you're seeing the speed of the wave on the wire, right? That information can only propagate at a certain speed. 3 seconds, right? The fact that the wire was propagated out to these locations. And 4 seconds out to these locations. So you could look at this and you could figure out coarsely what the speed of the wave is, right? So this was 2 seconds. In 2 seconds, I took half of this, the wave has gone maybe 10 or 15 centimeters, something like that. We could check that against what we calculated for the speed of the wave. So we're seeing the wave travel, and then, after some period of time, you see this, again, kind of sawtooth propagating along the length of the wave, along the length of the string. I did one more thing. I won't run this cell or go into the details of the animation, but I made a little animation of it here. And we can at least take a look at that. I think it's moving. Maybe, yeah. I got 10 millisecond intervals, so it's it's like slow motion.
I know it's moving.
Yeah. Here it's moving along the length of the wire. Look, it can't. Here's the boundary condition. So it's being reflected off that wall there. And depending on whether you've got fixed ends or open ends, you get different types of reflection. You might get a reflection here with the opposite phase of the wave. A reflection with an open string might be reflected with the same phase as the incoming wave. It's kind of like, if I'm remembering right, the reflection of different refractive indices materials, depending on the one that you're in, going towards, the reflection either changes phase or doesn't change phase. And for a wave on a string, the reflection either changes phase or doesn't change phase, depending on whether the string is open or closed at a particular end.